Welcome to Study Loop.
In this problem, the forces acting on the beam are the tension in the cable, let's say TC, and the tension in the rope, TR. Now, for the hanging mass to be in equilibrium, the tension in the rope must be equivalent to the weight of the hanging mass mg, or TR equals 20 kgs times the gravitational acceleration of 9.8 meters per second square. So the tension in the rope is of magnitude 196 newtons. Now, to find the tension in the cable, first we need to draw the free body diagram of the beam, and the forces acting on the beam are the weight of the beam acting through its midpoint, that is capital Mg, and the tension in the rope along the vertically downward direction, and the tension in the cable acts horizontally towards the left direction, and at point O the reaction force is Ry along the vertical direction and Rx along the horizontal direction. Now this is the point O. Now from point O, the horizontal distance of the weight of the beam, this distance will be half of the length of the cable, that is 1.5 meter. And from point O, the distance of the tension in the rope will be equivalent to the length of the cable, that is 3 meters. And the distance between the tension force and the tension in the cable and point O is given as 4 meter. And if we consider along the clockwise direction as positive direction for the moment, so for equilibrium, the summation of all moment about point O equals 0. Or we can write mg times its distance, that is 1.5 meters, plus the tension in the rope times 3 meters minus the tension in the cable times 4 meter equals 0. Or the tension in the cable equals 1.5 mg plus 3 times the tension in the rope over 4. Now let's substitute the values. So the tension in the cable equals 1.5 times the mass of the beam is 50 kg times 9.8 meters per second square, plus 3 times the tension in the rope, that is 196 newtons over 4. So the tension in the cable equals 331 newtons. This is the solution for part A, and the tension in the rope is 196 newtons. Now for part B, for equilibrium, the summation of all forces along the x direction will be 0, and we consider x direction along rightward horizontal direction and y direction as vertical direction. So we can write the reaction force Rx minus the tension in the cable as 0. So the horizontal reaction force is equivalent to the tension in the cable, or the x component of the reaction force is of magnitude 331 newtons. For vertical equilibrium, the summation of all forces along the y direction will be 0, which means Ry minus the weight of the beam minus the tension in the rope equals 0, or Ry equals mg plus the tension in the rope, or that equals 50 kgs times 9.8 meters per second square plus 196 newtons, or the vertical component of the reaction force is of magnitude 686 newtons. Now the resultant reaction force is given by square root of Rx square plus Ry square, or the resultant reaction force magnitude will be equivalent to 762 newtons, and the angle made with horizontal is given by tan inverse of Ry over Rx. So the angle theta of the resultant force with horizontal will be 64.2 degree above horizontal.